The result we obtained in Borexino yesterday, unfortunately this paper was not visible. I converted it simply in a PDF. So this is the special spectrum we are looking for. This is the beryllium 7 events.
But they have with
Okay. This is the beryllium 7 we are looking for. This is carbon 14. This is carbon 11 due by cosmic muons. So the total spectrum we have, okay, is this one. This is all data, and once we get only the inner part of the detector, I mean, we keep only the first 3 meters, we obtain this one. Wait. Okay. This is the spectrum. This is obtained only in the future volume. Okay. And you see that is a big peak, the alpha peak. The carbonium 14 is always here, and do nothing. This is the alpha particle, but as I said yesterday, we can discriminate between alpha and beta. And once we discriminate this peak, we obtain. Wait. Okay. After the alpha subtraction, we obtain this spectrum in red. And once we have this, we apply a fit with the expected contribution of all the neutrinos and background, and actually we obtain the data. This is the spectrum, this is the fit. Just a moment, okay. And we fit the last spectrum to obtain this data. Actually we obtain 39 plus or minus 3 count per day per ton, as expected by the solid standard model.
This is the red line?
The red line. This, for example, is 395, you can see here. The other is carbon 11, carbon 10, and so on. And by fitting, look at the square, you can obtain how many events you can infer for this contribution.
So it is important that the background is going like this, right?
Sure.
In order to have this
complement.
Yeah. This deeper.
You can see here is the energy. Before we have, if I go back this way, oh, anyway. Go back. This is photoelectron, I mean, how many light you see, but we have to calibrate in order to understand to which photoelectron corresponds for one deposited energy. If you cross-check with carbon 14, you discover that you have about 500 photoelectrons per MeV. So we are able to put an energy on this scale, as we see in the last transparencies. Okay, this is energy. But for sure the energy is not very well known. Okay. So, beside the 3 count per day with the error bar, this is statistical error, we have to add also systematic error. And we have a big error for what concerns the energy calibration. I mean, we say that 500 photoelectron plus or minus something. We have to calibrate in order to say that. The fiducial volume. So the total systematic is about 8.5%. This means that we know the count of beryllium 7 with this error. 3 statistics for the systematic. And if you compare with the expected one is quite well. We found was expected.
Ines, can you tell us how you calibrated the detector?
It's a longer procedure. In order to do that, we plan to put inside the balloon some laser, light, in order to reconstruct the exact position. Because you see, when we give the count in tons, if you have the diffusion mass that change just a little, this is cubic, means we have a big error on the mass. So we have to calibrate by, we put sources, laser or for example spike radon source in order to have light in a position that we know, and we reconstruct position knowing the exact position. I mean, we can cross-check how many confident we are in our algorithm of position construction.
Yeah, but this is the position reconstruction, but the calibration of energy.
The calibration of energy is made with the radioactive source, but the problem is that for what concerns light, I have to write it. The problem is that
loud.
A little bit louder.
Speak louder?
Yeah.
Yes.
Okay. So, when you calibrate the detector, you have, for example, in case of a scintillator, we have, for example, light versus energy. Okay. For example, this is dl over x, here is E over dx. So you expect that if the detector, the response of the detector is linear, you expect something like that. Okay? If you double the energy, you double the light you have. But in principle, because at a very low energy, starting from about 300 kV, this curve is the more aligned, but become this wave. So you have to gauge in a different position and in this. Okay, because you have, if you want, I can explain because you have this.
Excuse me, I have a question. When on the beginning of your lecture, it seemed for me that you showed us expected rates. It was 45 events per day per 100 tons without oscillations. And with oscillations, there were 30.
Okay.
30.
But in the other case was, as I said, between 250 and 800 kV neutrino windows. This is this is the total.
Oh, okay.
I will say that usually you write this is equal is dE over dx divided by 1 plus kb. This is the Birk parameters multiplied by dA over dx. This is square, if I remember well. Any case, if this one is 0, you have a direct proportional between light and energy. But because of this parameter that you don't know, depending on the scintillator itself, you have to calibrate different position and not just two in order to align. This is the actual difficulty to calibrate the different things. So we plan to, for sure, have more statistics, but the best thing to do is to know the energy calibration and to reconstruct the exact position.
May I ask you another question? Can you go back to the previous slide where you have these different contributions on background? Yeah. So from first glance, maybe it is wrong, but that krypton background looks quite similar to the signal.
This is a very common.
Right.
Yesterday I skipped the slide about krypton 48, krypton 85. So I can go back. Because it's a beta decay with an endpoint of 600 and something. just to show the krypton. Okay. Yeah. Krypton decay